Okay, a very good afternoon, everyone. So we will continue our discussion today on root locus. So we'll start with this problem, and then eventually we will move forwards. So the question is, you have an open loop transfer function with gain k s plus 5 divided by s into s plus 13 into s plus 2. It's a 2 here. and and we have to plot its root locus. There are many questions, but we'll eventually answer all of them. So, what are the number of poles? We have 3 poles, 0, -2, and -13. So P is equal to 3. Similarly, zeros, Z equal to -5. We have 1 0. Okay. So what is P minus Z? P minus Z is 3 minus 1, which is 2. Okay. Now let's try to plot the stuff on S plane. We have 3 poles. One is at 0, other one is at 2, other one is at -13. Okay, so now we have to see which is the valid part of the locus. So for that we see we select a pole and see the right part of it. We have already discussed it in the last lecture, so I'm not going into details of it. So we'll see this part is a valid part of the root locus. This part is not a valid part of root locus, and this part is a valid part of root locus. Okay, fine. Now let's see what are the number of asymptotes. Right, so we have 2 asymptotes because P minus Z is 2. So we have 2 asymptotes. And the angle of these asymptotes is given by, so let's assume theta of asymptote, it's given by 2q plus 1 into 180 divided by P minus Z, where q is equal to 0, 1, so on up to P minus Z minus 1. So in this case, we have q equal to 0 and 1, and when we put q as 0 and 1, we get the angle of asymptotes 90 degree and minus 90 degree or 270 degree. Okay, now we have to find the intersection of these asymptotes on the real axis, and that's given by centroid. Okay, you have to follow steps. And what is the formula for centroid? We learned that in the last lecture, which is given by summation of real part of poles minus summation of real part of zeros divided by P minus Z. And we have 3 poles, 0, -2, -13, minus, we have 1, 0, a -5, P minus Z is 2 divided by 2, which will be 7, it's 20, -20, No, it's not minus 20. It is plus 5. Yes, minus 5. It's minus 5. Okay. So we got centroid as minus 5. Now let's locate this centroid. Okay. My centroid is at minus 5. So this was my 0. This was my minus 2. And this is my minus 13. So my centroid is somewhere here. Okay. This is minus 5, my centroid. So at this centroid, I will make the asymptotes, which will be one is 90 degree, other one is minus 90 degree. Okay. Okay. So this is my these are my asymptotes. Now let's move forward. We have to now if we see the root locus, that will be something like this. This is a valid part of root locus. Valid part, and there will be a breakaway point. Similarly, this part is, oh, I'm sorry, I did not. Okay, there is one more thing. I need to. There is a 0 as well. There is a 0 as well here. At minus 5, I had not plotted that on the real axis. So we have to plot that as well. Okay, so this is my 0. So my open loop poles, they will converge to open loop zeros. I have 3 open loop poles, so among which the 2 will go to infinity and 1 will converge at minus 5. So we can see this pole, this clearly converges at minus 5 here. Fine. And these 2 poles will go to infinity and they will break at a breakaway point, which we will find shortly, and go to infinity via asymptotes, which we have already the angles of which we have already calculated, and the intersection of these asymptotes with the real axis, that's also calculated. Now we have to see the breakaway point. We'll find breakaway point, and how do we find breakaway point? So for breakaway point, we find the expression of k and differentiate it, put it equal to 0, find the value of s, then see whether that is a valid breakaway point or not, because for the point to be a valid breakaway point, it should lie on the root locus, right? So if we see from this expression, we can find the value of k. So breakpoints, we'll find the value of expression of k, which is given by minus s cube plus 15s squared plus 26s divided by 2 into s plus 5. So if we differentiate it with respect to s and put that equal to 0, we will get s cube plus 15s squared Yeah, hello. Now am I audible? Is my screen visible as well, Suraj? Okay, fine. I think then we can continue. Okay. If at any point you feel like my screen is not visible, let me know. Okay, so let me revise this question. So we were given a question, so where we had to plot the root locus, and we had three poles and 1 0. And first of all, what we do, uh, we right, see the number of poles and the number of zeros, then find the total number of branches. Uh, is screen visible to everyone? Suraj, can you confirm? Is screen visible to you? Dave Dubey, maybe you can just log off and then log in again to see the screen, maybe, because the screen is visible to others. Okay, so this is one question. Now we will just move forward and see angle of arrival and angle of departure, etc., etc. Okay. So in this question, if you see any pole, for example, this -2 or this 0, like there are two directions for this pole on real axis. Either it can go in the right direction or it can go in the left direction if this is a valid root locus, right? And then it will go to infinity. But if you have a complex pole, for example, we have a complex pole here, and this has to go to infinity, or it has to converge to some 0. Then there are n directions. There are n directions. In direction number 1, direction number 2, 3, 4, n directions are there. And which direction it will choose and how it will go to that particular 0 is given by the angle of departure. So how this pole departs and converges to either infinity or at some open loop 0, that is given by angle of departure. Similarly, when we have a 0, complex 0, and how our open loop pole arrives at that 0, there are n number of ways of arrival to that complex 0. And that is given by, and how that arrives is given by the angle of arrival, right? So mathematically, I'll just write the formula. So mostly we'll be doing angle of departure. So mathematically, angle of departure is given by pi d, which is equal to 180 plus angle of GH dash. I'll tell you in a minute what is GH dash. And angle of arrival is 180 minus angle of GH dash. And what is GH dash? Where GH dash is the transfer function, where GH dash is the transfer function by removing, obtained by removing that part of complex pole or 0, because for angle of arrival, we will have a 0 at which the angle of departure or arrival is calculated. And this will be clear in a minute. I'll just explain it through an example. Might be confusing as of now, but yeah, it will be clear in a minute. Just let's try to solve this question, or in particular, let's find the angle of departure uh, uh, in this case. So we have GH, which is given by K into S plus 1, S plus 2 minus J, S plus 2 plus J. So we have a transfer function where we have no complex poles. So we have no zeros, we have complex poles. It means our these complex poles, they will converge to infinity. And how they will converge to infinity is given by the angle of departure, right? So we will find that. See, so first of all, there are three poles. One, sorry, -1, -2, minus j, and -2 plus j. So these are the number of poles, and we have to find the angle of departure for the complex pole s is equal to -2 plus j. So for this complex pole, we have to find the angle of departure. Let's first plot it, and then it will be more clear how I will apply the formula. This is my S plane. So I have two poles. One is at -1, one is at -1, and other one is at -2 plus j. Other one is somewhere here, other two poles. Right? I converge. Now uh, uh, we have to find, because now these poles, they will go to infinity, or they will go to infinity via some angle which is called angle of departure, which we will calculate. So let's assume this is -2 plus j, and this is -2 minus j. Now we have to find angle of departure for s equal to -2 plus j. We know that is equal to 180 minus angle, 180 plus angle of GH dash. Now we have to make this GH dash. How we will make it? For the pole where we are calculating it, we will remove that in the transfer function, and the net transfer function we get is angle of GH dash, and we have GH dash, and we have to find the angle of that transfer function. So let's find a GH dash. So GH dash will be K divided by S plus 1. Now we have to remove this pole. So it means it will be, if I write it, it will be S plus 2 minus j. So s plus 2 minus j means this part. So this part I'll remove. I'll not write it. Okay, I'll write the other part, which is s plus 2 plus j. If you have any doubt, just let me know. So I wrote this part. Okay, now we have to find this angle. We have to find angle of gh dash at s equal to -2 plus j. So it means I have to put s equal to -2.j, which is equal to k divided by -2 plus j plus 1. There are other ways as well to calculate this angle, but this is the most simple and straightforward. -2 plus j plus j. Okay, now I just did one thing. I just put the value of s. Now what we will get? Angle of GH dash at s equal to -2 plus j is equal to k divided by, this will be -1 plus j into -2. Sorry, here I need to, okay, I need to put value properly. So I have -2 plus j, then +2 plus j. 2 and -2 will go, and I'll get 2j. Now we have to find the angle of this. How do we find the angle? I told you in the last lecture, we directly see from the coordinates. So this is in the second quadrant, this is in the first quadrant, right? So my angle of GH dash at S equal to -2 plus J, it will be equal to 0 for numerator, minus for denominator. This is in the second quadrant, 180 minus tan inverse of 1 over 1. Then for this, it will be plus 90 degree. Okay, and tan inverse of 1 over 1 gives 45. So it is equal to 0 minus 180 minus 45 plus 90, which is equal to -225 degree. So now we can find angle of departure phi d, which is given by 180 plus minus of 225, which is given by minus 45 degree. So we got the angle of arrival departure to be minus 45 degree. It means, so it means this pole, so minus 45 means somewhere here. So this is minus 45. So the angle, so it will leave from this pole like this. Then it will go to infinity towards asymptotes. But as of now, we just have to find the angle of departure. So angle of departure will be minus 25 clockwise, or if we have to find what will be this angle counterclockwise, if we calculate it like this, it will be 360 minus 45 degree. Okay, so this is how, because this question is only about finding the angle of departure or angle of arrival in general, but in questions we will be using this. So I just told you how we will apply, how we will calculate, but this will just be a step in our root locus, questions. So if this is clear, let's solve one good question where all these concepts will apply. Now let's solve this question. We are given g of s h of s k divided by s into s plus 6 into s square plus 4s plus 13. So we are given this question and we have to sketch the root locus, right? So we will find breakpoints, angle of departure, and also try to find the stability condition, right? So as of now, we just have to plot the root locus, right? Complete root locus. Now solution. Number of poles, 3. Sorry, number of poles, 4. What are these? 0, minus 6, and minus 2 plus 3j, comma, minus 2 minus 3j. If you solve this part, you will get these complex poles. Okay, so you got 4 poles, minus 2 complex poles, which are minus 2 plus 3j and minus 2 minus 3j. And there are no zeros. Number of zeros is 0. It means P minus Z is 4. It means we have 4 asymptotes. So asymptotes are 4. And angle of asymptotes, no need to calculate, because I already told you when you have 2 asymptotes, the angle of asymptotes is 90 and minus 90 degree. Similarly, when you have 3 asymptotes, it's 60, minus 180, and minus 300. 60, 180, and 300, right? Similarly, when you have 4, because all the time this calculation will be same, right? I can directly write the angle of asymptotes. So angle of asymptotes theta will be 45 degree, 135 degree, 225 degree. It's not a big deal to calculate. 315 degree. It's not a big deal to calculate. You just have to put in the values in this formula. 2k plus 1 divided by p minus z, where q is 0, 1, so on up to p minus z minus 1. Okay, so we directly found the angle of asymptotes. Now we have to see the intersection of these asymptotes on the origin, which is given by centroid. So I'll calculate centroid. Centroid is given by summation of real part of zeros minus summation of summation of real part of poles minus summation of real part of zeros divided by p minus z. So we have summation of real part of poles 0 minus 6 minus 2 minus 2 minus summation of real part of zeros is 0 minus 0. I'll directly write 0 divided by p minus z is 4 minus 0. It's minus 10 by 4. So it means my centroid is given by minus 2.5. Okay, so this is my centroid. So now let's try to plot it. Let's try to plot it. Okay, so we have 4 poles, right? So we have 4 poles. One is at 0, other one is at -6. This is -6, and other two are -2 plus J3. So somewhere here, and other one is somewhere here. Okay, wait. So one is here, and other one is here. Okay, I just plot this. Now we have to see centroid. Centroid, so this is 2 -2 here. And my centroid is -2.5. So my centroid is somewhere here. My centroid is somewhere here, which is -2.5. And at centroid, I have to plot angles. As the centroid gives me the intersection of asymptotes. So at this centroid, I will make 4 angles, which is given by 45, 135, 225, and 315. So at this point, I'll have angles like this. Okay, so this is 45. Similarly, this is 135, and this is how much? 215, I think. 225. 225, and then we have another one, which is this, which is 315 degrees. So I'll not mark these angles. It's not looking good. So I hope you understand this. So these are my asymptotes. They should be straight. So okay, let me make them a bit straighter. Okay, so these are my asymptotes. Now we will find, or we'll see. Now we will see which is the valid part of root locus. So you see, this is a valid part of root locus. If we see this area, my root locus will come like this. Because on real axis, a valid part of root locus is the number of poles on the real axis should be odd to the right of that pole. So now there has to be a breakpoint. So we will find that breakpoint. So how we will find that breakpoint? We will find the breakpoint from the expression of k, right? So now let's find breakpoint first. So if we find the expression of k, we will get expression of k as minus s4 plus 10s cubed plus 37s square plus 78s. And if we differentiate it with respect to s and put equal to 0, we will get some equation, and finally we will get the value of s, which is satisfied. The valid breakaway point is minus 4.2. I have skipped. You can directly find the solution of this equation. 4s cubed plus 30s square plus 74s plus 78 equal to 0. There you will find 3 roots, out of which only 4 minus 4.2 is a valid breakpoint, because it has to lie on the root locus. So that means this point lies somewhere here. This is my breakpoint, which is minus 4.2. Okay, so this is my breakpoint. So it means my root locus, it comes like this, comes like this. Then it breaks here. So it breaks here and goes to infinity along this asymptote and goes to infinity here from this along this asymptote. This is fine. So this part of root locus is clear. So two poles, they went to infinity through asymptotes. This asymptote and this asymptote. Now we have these two complex poles. They will also go to infinity, but how they will go to infinity? There are n number of directions again. So I told you we have to calculate angle of arrival, angle of departure. So the angle, how they will go to infinity will be given by the angle of departure. And I told you in the beginning, in the previous class, that root locus is symmetric towards real axis. So if I calculate angle for this, if it comes 30°, then for this pole, it will be minus 30°, right? So if a complex pole lies on root locus, then its conjugate part also lies on the root locus. Why? Because root locus is symmetric on real axis. Now what we will find, we will find the angle of departure for these two complex poles, which are +2 minus 3j and minus 2 plus 3j and minus 2 minus 3j. So now let's find angle of departure, right? So we have to find angle of departure for this pole, which is minus 2 plus 3j. I told you it is given by 180° plus angle of GH dash at S equal to minus 2 plus 3j. And how we find GH dash? We have to remove this minus 2 plus 3j from the transfer function, right? So we have to remove this, then we will get the required angle of GH, right? So now let's do it. So what was our transfer function? So we need to find GH dash, which will be given by K into S plus 6. Now we have to remove this part. So I will get S plus 2 plus 3j. I removed this part. Why? Because it will be S plus 2 minus 3j. This I removed, and now I will put, for the angle, I will put S equal to minus 2 plus 3j in this equation. Okay, now let's find the angle. So I will get K divided by minus 2 plus 3j into minus 2 plus 3j plus 6 into minus 2 plus 3j plus 2 plus 3j. This 2 and this 2 goes. So what we will get? Angle of GH dash is equal to K divided by minus 2 plus 3j into 6 minus 2 is 4 plus 3j into 3j plus 3j is 6j. Now let's find the angle. The angle is given by 0 for numerator, minus for denominator. Now, what is the angle of this? It's in the second quadrant, so it is 180 minus tan. I hope this is already clear because I explained it in the previous lecture. It's in the second quadrant, then plus for multiplication. So plus, it's in the first quadrant, tan inverse of 3 by 4 plus 90° because there is no real part. So tan is infinity at 90 because this will be infinity. So if we calculate it, we will find this will be 0 minus 180° minus tan of 3 by 4 is 36.86°. 3 by 2, sorry. 3 by 4 is 36.8 degrees. So this is plus 90°. And for this part, minus tan inverse of 3 by 2. So it will be just find from the calculator tan inverse of 3 by 2. 56.30. 56.30. 56.30. Okay. So when we solve it, simplify it, so we will get this angle of GH dash to be 180 plus 36.86 plus 90 minus 56.30, which we are getting as 250, right? 250.56 minus 250.56. Now, this is my angle of GH dash. Now, how to find angle of departure? My angle of departure will be 180 plus angle of GH dash. It means which is equal to 180 minus 250.56, which is equal to minus 70.56. So my angle of departure will be 70.56, right? So it means if it is how much is it? Minus 70.56. So for this pole, if it is minus 70.56, then this is the complex conjugate. This will also, this for this pole, it will be 70.56, the angle. Okay. So it means this pole will go to infinity by making angle 70.56. So that means it will go to infinity like this. Okay. Similarly, this point will make a angle of positive minus 70. So it means minus will be like this, positive 7.5. So this will be, then this will be like this. Make it like this. If you have any confusion, please tell me. So it will be somewhere like this. Okay, so you see this angle will be 70.5. Okay, so is there any question? Now, how do we do this? Because there is a formula for angle of departure. We just apply that formula, and that formula says angle of departure is 180 plus angle of GH dash. And GH dash is the transfer function obtained by removing that part of pole at which the angle of departure or angle of arrival is calculated. So that's what we did. Put the value of here, it's minus 2 point plus 3j, put it here and found we got this value, and subtracted it, got the angle of departure. And we know for complex since the root locus is symmetric along the real axis, so if this is minus 70.56, then this is plus 70.56, and this is how it goes to infinity. I hope this is clear. If there is any question you can ask at this point, or we will just move on. Before the next question, before I proceed for the next question, let me give you one important formula which might help you. So sometimes you get a circle. Sometimes your root locus diagram is a circle. So when is that a case? So if your G of S, H of S is of this form in general, K into S plus B, S into S plus A. If this is the form with b greater than a, then your root locus is a circle with center. So I'm just writing the formula, but we will understand it from the root locus as well. So sometimes it's difficult to remember the formula, but I can tell you directly how you can calculate this directly from the root locus. So then the center is given by minus b comma 0, and the radius is b square minus ab. Now see, I'll just draw it. I'll just draw this root locus. We have a pole at 0, and we have a pole at a. This is minus a. This is 0. And we have a 0. We have a 0 at b, minus b, right? So now, which is the valid part of root locus? You know, the valid part, this is the valid part of root locus, and there will be a breakaway point, which we will calculate eventually. Now, this part is not a valid part of root locus, but yes, this part is a valid part of root locus, right? Now, can I draw it like this then? So from here, there will be a breakaway point, and somewhere here we have minus infinity. So between two poles, there is a breakaway point, and between two zeros, there is a break-in point. So you will get something like this. So this will go to infinity. This will converge to 0. So it will be something like this. See, it will go like this. Then reach here. One will go to infinity, and other will converge to the 0. So you found this root locus to be equal to circle. Why? Because there are two poles and they have to converge to open loop zeros, but there is only one pole. So one zero, one pole will converge to 1 0, the other pole will converge to infinity. And you will see it like this. And from here, you can see that the center is minus b comma 0, and the radius is b square minus ab. But this is not necessary to remember. Why? Because you see, this root locus, this point is what? This is breakaway point, and this point is what? Break-in point. So if you know break-in and breakaway point, you can easily find the center. How? The center will be the midpoint of this break-in, and you take the distance from break-in and breakaway point. The midpoint of that will be center, right? Very simple. And when you know the center, you take the distance between break-in or breakaway point. That is the radius. So this part. So if this is breakaway point, this is breakaway point, and this one is break-in point. So we can see from here, this distance is the radius. Similarly, this is not symmetric, this part, but it has to be like that. So this part is the radius. So you can directly calculate it from here. Take this point, you know this breakaway point, this is center, you know this, just take the distance and you're done. Right? So now based on this, let's do one quick question. There are good questions normally which come in GATE based on this, but let's do this question. Yeah. Now the question is, you have g of s, which is given by k into s plus 6 into s plus 4. So this is your g of s, and the question is given as the feedback control system has g of s as this, and an ideal integrator with a unity gain in feedback path. So h of s is 1 by s with a unity feedback. So with a negative feedback. So determine, then we have to find the root locus. So h of s is 1 by s, then your g of s h of s, it will be simply g of s h of s, and cascade will be k into s plus 6 divided by S into S plus 4. Now, as of now, I told you, if you have you can directly see it from the formula, or you can just plot the root locus. Both ways, you can reach at the same conclusion. But let's assume we don't know anything about this thing, which I told you right now. Let's say we don't know it. We'll just plot it from the scratch. So now let's see root locus. So we have two poles, S at 0 and -4. We have 1, 0, which is at -6. Correct? So how many number of asymptotes will be there? P minus Z is 2 minus 1, which is 1. So it means there is one asymptote. And now let's plot this thing on the root locus, like on the S-plane. So we have one pole at origin, other pole at -4, and a 0 at -6. Perfect. So this is 0. -6, this is -4, this is 0. Now see, this is minus infinity here. This part is a valid part of root locus. This part is not a valid part of root locus. You know it. No need to explain. And this part is a valid part of root locus. Okay. Now let's make the root locus. Again, just remember, between two poles, there is a breakaway point. Between two zeros, there is a break-in point. So my root locus will start somewhere here. And also go to somewhere here and also go to infinity. It will be something like this. So there will be a break-in point here and breakaway point here. So now let's first calculate this break-in point and breakaway point. We know it. How do we calculate break-in point and breakaway point? We calculate it from the expression of K. So we have 1 plus K into S plus 6 divided by S into S plus 4. We put it equal to 0. We find K is equal to minus S into S plus 4 divided by S plus 6. Now, if we differentiate it with respect to S and put it equal to 0, we find some big equation, and eventually we'll get this equation: S squared plus 12S plus 24 equal to 0. Now, if we solve it, we'll get S equal to minus 2.536 and minus 9.464. Now, after this thing, we have to see whether these points lie on the root locus, lie on the root locus or not. If they don't lie, then they are not valid breakpoints, or if they lie, then they are valid breakpoints. So our breakpoints are minus 2.5 and minus 9.4. Now see, minus 2.5 will lie somewhere here, so it is a valid part of root locus. So it means my breakaway point is minus 2.5. Similarly, my minus 9.4 will lie somewhere here. So it means that this is also valid because this lies on the root locus. So minus 9.4. Okay. So this point is a break-in point and this point is a breakaway point. So here I can see my this root locus diagram will be something like this. Okay, my root locus diagram will be something like this. Okay, I'll make it more better way. I'll make it from this direction. Okay, now see, they come like this and converge here. Then one goes to infinity and other one comes to this 0. Now you have to find the center of this. Now, if you have to find the center of this circle and also the radius of the circle, how would you find it? Very simple. First, see, my break away point is minus 2.536. My break in point is minus 9.464. What is the distance between the two? So What is the distance? Very simple. Your distance is plus 9.464 plus 2.536, 12. So the distance is 12, right? And the midpoint will be divided by 2. The distance divided by 2, right? So this distance divided by 2. And eventually, if we see, it is in this form. It is in this form. It's directly in this form. So we can directly write my center is minus b comma 0. B is 6. So my center is minus 6 comma 0. And radius is b square minus ab under root. But you can see from here, so this is your breakaway point, this is breakaway point, this is break-in point. You just take the distance between these break-in and breakaway point, sum that up like that distance, and take a midpoint of that distance, which will be given by 6. This is not properly drawn, but you can draw it properly. If you see from the MATLAB, then things will be more clear. So it's very easy to see from the root locus itself how you can find the radius as well as the center of the circle if it is a circle. Okay, so let's do one more question. I hope things are getting clear. It's not a things will be more clear by practicing more and more questions, right? So there is one question which looks difficult, but yeah, you have to solve it based on the similar circle concept. So you have R of t. I'm making a control diagram, like closed loop control diagram. In gate, you will get questions like this. There will not be any single question where you will be asked to find the root locus. They will be like this. So you are given a diagram, a closed loop unity feedback control system, right? So this GC is the controller, GP is the plant. And what is this GC? This GC is S plus 3 divided by S plus 1, and GP is K into S plus 2 divided by S. Now find the root locus. Or sketch root locus. It's better to write sketch root locus. So how would you do that? For this question, how would you do that? And tell me what will be the shape, right? So very simple. Just follow the steps. Just follow the steps. Now, first of all, what we have to do, we have to take, since they are in cascade, let's find the net transfer function, right? So what will be net transfer function? Our G of S will be GC into GP. It's okay, right? GC into GP, which is equal to K into S plus 2 into S plus 3 divided by S into S plus 1. This is my GP, and they have two poles at 0 and 1. Please try to solve it. So you have two poles at 0 and 1, and two zeros at 2 and minus 2 and minus 3. So if you solve it, if you try to so I'll just locate it for you. You have 1 0 here, sorry, one pole here, one pole here, and so you have something like this. This is a valid part of root locus. This diagram, this is not. This is also a valid part of root locus. Now see, there will be a breakaway point. There will be a break-in point, right? So obviously it's a circle, right? Because the poles will break away here and they will break in. There will be break in here. So something like this. Then from here, it will go to this zero and this zero. So if I plot it, right? So something like this. Now just tell me what is the center of this circle. So for center, you need to find the expression for K. You need to find the expression for K. And after that, you will get dk by ds. Put that equal to 0. Please solve it. I'm just giving you a hint. So dk over ds, putting that to 0, right? And you'll get the value of s, which will be one will be break-in point, other will be breakaway point. Valid or not, you will have to see that. So when you get the valid break-in or breakaway point, from that you can easily calculate the center of the circle, and also the radius of the circle. These types of questions you might expect in GATE because nothing is given directly. You'll be asked, so what is the shape of this? You'll be asked like this. You're given a closed loop control system as shown in the diagram with GC and GP given as. The root locus of this will be, then there will be options: circle, ellipse, hyperbola, or parabola, right? And then the other question will be, uh, find the center. If it is circle, then find the center and radius of the circle directly. So in order to do that, in order to solve that or answer that question, you will require break-in and breakaway points. So entirely, eventually, you'll have to sketch the whole root locus. Right. So, but all concepts are coming. See, here is a concept of cascade, or you see root. You'll find open loop transfer function, etc. and etc. Right. So the answer will be, your center will be minus 1.5 comma 0, and radius will be 0.75. I think that will yes, 866. So this will be your answer. Now let's solve one last problem for the day, where again this complex stuff will come into picture, right? So one last question for today, which is, I would solve it quickly, assuming your things are very clear for you. G of s, h of s is given by k s into s plus 1, s plus 3. You have three poles, 0, minus 1, and minus 3. So you have to sketch root locus. Problems I'll keep on giving. So let's go on plotting. First, let's plot the root locus. There is no 0, so there are three asymptotes. And no need to calculate the angle of asymptotes. You directly know it will be 60, 180, and 300. So my angle of asymptotes will be 60, 180, and 300. Now the only thing you need to calculate is the centroid. Centroid will be summation of real part of poles minus summation of real part of zeros minus p minus z. So it will be minus 1.33. So you got centroid, you got this angle of asymptotes as well. Now let's plot it. See, so my poles are at 0, -1, and -3. -1, -3, right? So this is a valid part of root locus, and this is not a valid part of root locus, right? And then this is a valid part of root locus. You know it. I'm not going to mention it. Again, I'll directly write it. Okay. Now, see, the valid part of root locus lies between two poles. It means there has to be a breakaway point. So let's find this breakaway point first. Okay. So let's find this breakaway point. So how do we find this breakaway point? We just find the expression for k. So 1 plus k into s plus 1 into s plus 3 equal to 0. You will find k equal to minus s cubed plus 4s squared plus 3s dk by ds equal to 0 implies s. I'll directly write the values, minus 0.45 and minus 2.21. So we see this is -1, this is 0, this is -3. This part is not a valid part of root locus, so minus 2.21 is not a valid breakpoint, so I will go with minus 0.45. So my breakpoint is minus 0.45, and my centroid is minus 1.33. Oh, centroid is not this. Centroid is this. Minus 1.33. Okay, so I got breakpoint, I got centroid, I think I'm done. I can plot the root locus. Now see, at the centroid, I'll first plot the asymptotes. This is my 60. This is my 300. And this is my 180, right? So see, my root locus will come like this, come like this, come like this, and from here, it will break away. So it will break away and go like this. Similarly, it will break away, and go like this to infinity. And from here, we'll go to infinity, right? Very simple. Anybody has any doubt? Now, if I ask you, this root locus intersects this axis here. Can you tell me the value? Can you tell me this value where this root locus intersects my imaginary axis? Right? So for these type of questions where you are asked to find the intersection of the root locus with the imaginary axis, you need to find the expression, you need to find the characteristic equation, and then from the characteristic equation, you use Routh's criteria, right? So, and see and find the value of k for which the system is marginally stable, right? Because the root locus will be on the imaginary axis. Okay, so for marginal stability, we have row of zeros, or uh, we have 0 in the routes array, and then we find the value of k, and then with that value of k, we can find the value of s, right? So this has already been discussed when we discussed route criteria and their auxiliary equation and other things. So basically, I'm revising it again. So if you are asked find the intersection of root locus with the imaginary axis, so what you will do is you will find the characteristic equation, make route array, then find the value of k for which the system is marginally stable. Then from that k, you put the value of that k in the auxiliary equation, solve for s, and those values of s will give you the intersection with the imaginary axis, right? So this can be a very good exercise. So with this, I think you have understood this root locus in a good way. Just practice more and more questions. Things will be more clear, right? So basically, angle of departure and angle of arrival, you need to solve more questions to strengthen your concept. And we will again, maybe again, go through this root locus concept when we are designing lead and lag compensators. So we will design lead and lag compensators using this root locus technique. There we will also see. So this angle of arrival and angle of departure, there are other ways also to find these angles. Like we have to consider the angles from all other poles. So that's what I have done actually. I did it mathematically. We can also do that from the graph itself. So there is we will discuss that again when we will see the controller design or lead and lag compensator design. So then they will be more clear. As of now, I'll just request you to solve more and more questions to strengthen this concept, to also go through the assignment questions, to also go through the lectures. Because if you see your lectures, then things are like you're having a great content there. The professor is explaining in detail, and more or less the assignments are also based on the lectures. So I would recommend you do that. And with this, I'll just stop this lecture. If you have any doubt, please let me know. Thank you.